Today we will discuss on MEMS capacitive accelerometer. In my last lecture, last few lectures, I spent on MEMS piezoresistive accelerometer, a case study that is particularly for avionics application. We just described how a accelerometer is designed and then what will be the technology, fabrication steps and its characterization. And today I want to spend on another case study, that is MEMS capacitive accelerometer, that is for generalized application for defense and many other automobile sector also we require such accelerometer. So, MEMS capacitive accelerometer, a case study, that is the topic of discussion today. Now, the design specifications of that accelerometer is a range of the accelerometer is plus minus 10 G, over range is 30 G, that means up to 30 G there is no destruction of the device, it should withstand. Damping ratio is 0.7 to 1.2, natural frequency is 100 hertz, nonlinearity plus minus 1% full scale, resolution 0.02 G maximum and threshold is 0.01 G maximum. Operating temperature range is minus 85 to plus 40 degree C. So, now with this specification, how do we proceed to design a accelerometer which is based on capacitive sensing. Now, the structure of the capacitive accelerometer is shown in the figure here, you can see, and this figure is 3 modules. You can see in the middle piece is basically the sensing element and it comprises of a probe mass which is also known as seismic mass, which can move freely between 2 fixed electrodes. What are the 2 fixed electrodes? One is held at the top and another is held at the bottom, and there you can see in the bottom piece which is a fixed and a parallel plate electrode is configured here, and you can take the contact from the side wall or maybe some bond pads are ejected at the outside and from where you can take outside external connection. Similarly, at the top fixed electrode also there is a metallized plane which acts as electrode. So, then the fixed electrode top and fixed electrode bottom will form capacitances with the middle sensing element. Now, middle sensing element, you can see here a movable seismic mass because of the movement of the object whose acceleration we want to measure. So, this probe mass or the seismic mass will move either up or down, and accordingly the capacitance between the seismic mass and top electrode and bottom electrode will change. So, that change of capacitance will be the measure of your acceleration. That is the capacitive accelerometer principle which we are going to follow in this case study. Now, the differential change in capacitance between the capacitors is proportional to the deflection of the seismic mass from the center position. So, obviously, if the seismic mass which is at the central position, if it moves upward, then the gap between the top electron and seismic mass will be less, and the gap between the top middle seismic mass and bottom electrode will be more. So, that means in one case capacitance will increase, in other case will decrease. So, this differential change we are interested, so that we can eliminate some of the parasitic things. So, the differential change obviously is proportional to the movement or to the G value of the object on which this accelerometer is fixed. So, that is the basic idea and basic principle. Now, The advantages of such kind of structure are manifold, such as very low sensitivity to temperature drift, that is the basic property of the capacitive accelerometer we know, higher output levels. It can be readily used in force balancing. If you connect this accelerometer in a closed loop operation, so you can use it for force balancing mechanism, and high linearity is achieved. On the other hand, there are certain challenges on this kind of accelerometers. This we can say it is a limitations of capacitive accelerometers. What are those? There, electronics for the signal processing are more complex. In case of piezoresistive accelerometer, we saw that simple Wheaton's bridge is sufficient for pick up the signal due to the acceleration change. But here the signal processing, because capacitance change directly you cannot measure, you have to have an arrangement or interface electronic, so the change of capacitance is reflected either change of voltage or change of frequency in the output, which you can further process for your application. But that electronics is done, is available, but it is not so simple like piezoresistive accelerometer. Second point is sensitive to parasitic capacitances and electromagnetic interference, because electromagnetic interference, that is why nowadays people want the electromagnetic compatible circuit devices are required, because lot of electromagnetic radiations are available in your surroundings. So they may induce some electromagnetic field, and because of that you can get some sensing voltage which may hamper the actual signal coming out from the sensor because of the G variation. So that is why it is sensitive to electromagnetic interference also, as well as parasitic capacitance, that I have already discussed many times in earlier lectures. Now, this structure which you saw here, the 3-piece, this is basically fabricated using bulk micromachining technology. There is another kind of capacitive accelerometer available, which is basically fabricated from surface micromachining. Those are comb structure capacitive accelerator, comb like structure, that I explained in earlier lecture also. The case study which I am going to discuss today is based only on bulk micromachining technology. Now, there are several kind of structures available. One is known as cantilever structure, other is known as bridge structure. You can see here two diagram. In one case, the seismic mass is held with a cantilever, single cantilever. In other case, the seismic mass is held with the frame with the help of two cantilevers supported in the opposite side, so that it is just like a bridge. Okay. Now, there are some advantage, disadvantage of both the structures, and that we will see which structure is better for all respect, means performance, technology, fabrication, in all aspect which is better. So, cantilever structure and bridge structure, if you compare, then first let us concentrate on cantilever structure, where I am going to use a single flexure beam. The whole seismic mass is held with a single flexure beam. So, the single flexure, its width is B1, its length of the flexure, the cantilever, is A1, which is shown in the diagram, you can see here. So, A1 is the length, B1 is the width, and H1 is the thickness of the beam. So, A1, B1, H1 is known. M is the mass of the proof mass, the seismic mass in the center which is there, and E is the modulus of elasticity. So, that I defined earlier, what do you mean by modulus of elasticity, and L is the center of mass from the clamped end of the beam, center of mass of the seismic structure, seismic mass structure from the clamped end of the beam. This is the clamped end of the beam. From there, say center of mass, if it is here, so then that is the length L. So, if A is the acceleration, then with acceleration A, the seismic mass along Z direction, if we accelerate the whole structure, then the seismic mass will move, some displacement will take place, and that displacement is Z, which is given by this relation twice m a e b1 h1 q into 15 L a1 minus 5 a1 square minus 12 L square whole multiplied by a1. So, that is taken from literature with some analytical calculation you can make using this relation. Okay. How the relation is derived, details I am not discussing, this has been taken from some references. Okay. Now, if we know the Z movement basically of the mass, then we can easily calculate how much change of the gap, because top and bottom electrodes are fixed. So, if I know the Z, so in one case the gap between the two electrodes will be reduced by Z, in other case the gap will be increased by Z. So, accordingly parallel plate capacitance easily you can calculate. So, that capacitance change also easily you can calculate. Okay. From there you can get the delta C, which is change of capacitance. Now, in this kind of structure there is a problem. What is that problem? Is a cross axis sensitivity. So, now if this is the single flexure, single cantilever structure, now if you make an acceleration along y direction, say y direction is shown in the bottom in the diagram, z is vertical and x y in this plane of this table for example. So, there if we move this whole structure along x direction, then the movement or the position of the seismic mass will be along z also. Okay. If you move along x acceleration, x direction, the rotation of the probe mass will be this is the x along vertical. So, that some movement will be there along z also. So, that means this kind of structure will not give you that less cross axis sensitivity. So, along if you decide or if you design the whole thing for z axis acceleration, so because of this structure it is also sensitive to y direction acceleration also. So, you can see the configuration. So, if you push it along y direction, it will just tilted, and because of that, so the gap is also going to change. Gap basically if you move the structure along y direction or along x direction, so parallel plate capacitance that gap should not change, but here it is going to change, because you see this portion of this probe mass or say seismic mass will go up and this side will go down, because it is try to rotate along x direction. So, this kind of structure is not very good so far as cross axis sensitivity is concerned. So, we thought of a different structure which is double flexure the cantilever structure. So, here instead of one we have used a two flexure. So, under that condition, if you move along y direction or x direction, this whole seismic mass will not rotate along that direction. So, that means whatever the movement is there will be along z direction, either upward or downward. So, if you move it along this direction, then it will not show any upward movement or downward shape change. So, because of that you can reduce the cross axis sensitivity problem. Okay. So, now here again the displacement of the seismic mass is shown in the relation which is given below. Ma divided by E is the modulus of elasticity, B1 H1 Q, 15 L A1 minus 5 A1 square minus 12 L square whole multiplied by A1. The relation if you find, I think only difference is here it is a only Ma, in earlier case I think it is twice Ma. You can see the relation is a twice Ma here. So, that is the difference in the expression, and all the parameters M, A, E, B1, H1, L, A1 are known. So, if you know those, that is basically dimensional parameters. So, then easily you calculate Z, from there you can calculate the parallel plate capacitance. Now, this kind of structure is advantageous so far as cross axis sensitivity is concerned. Now, here if you look into the cross section of the structure, then also you can calculate the Z displacement from this relation also. That is, here you can see the thickness of the, this is a cross sectional diagram. H1 is the flexure thickness mentioned there, and H2 is the probe mass thickness, which is basically the wafer thickness, and F equal to mass into acceleration is a force, and I is the moment of the seismic mass. So, in terms of moment of the seismic mass, so Z, the movement along the, or the displacement along Z axis of that probe mass is given by this relation. Okay. And acceleration in x direction results in bending of the beam and the mass lifts up. Okay. If you use single flexure, motion of mass due to acceleration in x direction cannot be distinguished from mass motion due to normal acceleration. The deflection of the mass in z direction due to acceleration in x direction can be expressed mathematically as given above. That is, for your the cross axis displacement z. Okay. So, if you move this structure along x direction, how much is z direction it will move, that expression is shown here. Okay. So, this will give you some idea about how much fraction of the cross axis sensitivity is achieved with such kind of structure. Now, as I told you, there are two capacitance. How the capacitance changes, that is shown in the diagram. The red lines top and bottom are the two fixed parallel plates, that is top electrode and bottom electrode, and the middle one is a sensing element. So, now with the movement of this whole structure, the seismic mass will go upward or downward. So, depending on its acceleration or deceleration, and then the d naught is the maximum deflection from this point to this point. For example, maximum deflection d naught, average displacement is shown here. Average displacement of the that means gap change between the fixed and the bottom, because this how much moves in up and down, that average value is d naught basically. Now, C1 is the capacitance with the top electrode and seismic mass, and C2 is the capacitance between bottom electrode and seismic mass. So, now the C1 is equal to C2 is C naught when the mass is at rest, that is obvious. So, when this is, there is no movement of the structure which is a rest position, the C1 will be equal to C2. So, if you move or under G, only the C1 C2 will vary. So, this is the capacitance variation, how it varies, you can see from this diagram. Now, with acceleration movement of the mass, that is basically like a fan, is to move up and down, and between the fixed electrode and movable electrode can be found out by integration along the length. Now, the one point is evident here, that you see, although we are telling parallel plate capacitance, the gap between top electrode and the middle is not same everywhere, it varies. So, that is why the capacitance is calculated by integrating from A1 to A2, where A1 is this distance and A2 is the from this point to this distance. So, from A1 to A2, if you integrate this relation, that will be the average value of the capacitance C1. Similarly, C2 is also A1 to A2, and it is given by this expression. So, it is not exactly parallel plate. So, directly straightforward the simple relation you cannot use it, isn't it. So, that is why the d naught is some average value, from there how much it is deviating. So, that is given by this relation. Now, the net change in capacitance can be found by finding C1 minus C2, and it can be expressed as delta C, which is C1 minus C2 is given by this relation C naught into twice A plus A2 minus A1 into B by D naught, where A multiplied by A plus A square by D naught square. Okay. So, this equation has a linear as well as a non-linear part. The second term is a quadratic term, is not exactly linear. Now, the sensitivity and non-linearity, these are another two parameters which we are also interested, because in our design specifications non-linearity has been expressed less than 1% of the full scale, sensitivity is 0.02 G. So, for that also we have to calculate the sensitivity as well as non-linearity of the devices. So, those are analytical expressions for those are given in this view graph here. So, it is sensitivity is delta naught divided by C naught into A, where this, if you put the value of the delta C, which is given in earlier expression, then the sensitivity expression comes like this. Similarly, nonlinearity is given by twice A square m 3 root 3 D naught square multiplied by this factor. Okay. So, these are the sensitivity and nonlinearity expressions from where you can easily calculate the values of sensitivity and nonlinearity. Now, the cantilever beam mass structure is a continuous system. The free vibration frequency is found using the Rayleigh-Ritz method, and the whole structure has got some natural frequency. That frequency depends on the dimension of the structures, thickness, mass, and the area, that means length and breadth, and modulus of elasticity. All those things depends, all those things will decide the natural frequency or vibration frequency, and that omega naught is given by this relation 1/4 the under root E B1 H1 q divided by m L square A1 multiplied by 1 plus 1.25 A1 by L plus 1.08 A1 square by L square. Spring constant K effective may be expressed as K effective, because from there you can calculate under root the relation of the mass and spring constant will be given by the acceleration. So, that is equal to E beyond H1 q divided by 12 L square A1 into 1 minus A1 by L plus A1 square by 3 L square. Detailed derivation of these expressions are given in literature. You can find those literature or any book on the mechanical vibration book, and there you can get these expressions of the natural frequency and the spring constant. Now, the deflection of proof mass in case of bridge structure. So, bridge structure is basically the seismic mass is held between two flexures. Now, you can see the flexures which is connected the seismic mass with the frame, that is not always at the top surface or at the bottom surface. The diagram shows it is at the just central position. Similarly, here also, and it has been observed by analytical calculation or the finite element analysis that if you make the flexure at the middle of the cross section of the seismic mass, it gives better response compared to the flexure fabricated at the flat top surface. So, there are different kind of bridge structures available. In one case it is held by 2 flexures, and in other case it is held by 4 flexures like piezoresistive accelerometer. Now, in both the cases, the deflection of the proof mass, which is given by the Z, is given by the simple relations which is shown here, and here also the H1, A1 and B1 are respectively the thickness and length and width of the flexures. M is the mass of the proof mass and A is the acceleration is the modulus of elasticity. So, the simple relation for the deflection, proof mass deflection for 2 flexure bridge and 4 flexure bridge is shown below. Now, in these kind of structures, the moment of mass is parallel to the fixed electrode like a piston, because it moves up or down like piston because it is held by 2 flexure. So, it is not the bending is not asymmetric, is uniform. If you held by 2 flexures, then either thing will go up or down like piston. So, now there delta C is given by C1 minus C2, which is again shown by this expression twice C naught, x by d naught 1 plus x square d naught square, and sensitivity and nonlinearity are also shown in by this expression for this kind of structure. Natural frequency f equal to 1 by twice by k by m, and the stiffness constant k is given by this relation twice E B1 H1 Q by A1 Q. Okay. These are the relations of sensitivity, nonlinearity, and change of capacitance, that is differential capacitance in case of 2 beam bridge structure. Now, next is coming the damping analysis. So, damping analysis is also important for stability of the structure, and there always we think of that the squeeze film air damping. These are top electrode and there is a bottom electrode, and this is the middle, this is a cross sectional structure, this is a middle seismic mass. So, gap is filled with air. So, air will flow in this direction. So, automatically the air pressure will obstruct the movement, and damping will be exerted on the structure, as a result of which it will settle after some time. Otherwise, if it is a resonance, there is no damping, it will not stop the vibration, it will continue. So, now damping coefficient C has been calculated as 2 into 0.42 mu A2 square divided by d naught q, and the xi, which is damping ratio, is C is the damping coefficient divided by twice m. M is the mass of the proof mass, omega naught is the frequency, natural frequency of the structure, which is again expressed C by twice under root mk, and is given by this relation, where mu is the viscosity of the damper here, which is the air, and all other parameters A1, H1, B1, M, E are known. Okay. Now, this is the damping expression. The damping ratio xi should be in the range of 0.7 to 1, in that 0.8 or 0.85 is the some desired value. So, with this expression you can calculate the damping coefficient as well as damping ratio of the complete structure. Now, with certain values we have calculated using these analytical relations, and also we have calculated using Cantilever software. Both are done, and we have seen how close they are. So, for a structure where the beam is the 90 micron H1, that is thickness of the flexure, B1 is 240 micron is the width, and A1 is the 600 micron is the length of the beam, and proof mass is thickness is 575 micron, that is 570 micron thickness, this is wafer thickness. B2 and A2 minus A1 is basically B2 is the width of the mass 4000 micron, and A2 minus A1 you can see the length of the proof mass, which is again 4000, that is square seismic mass you are using 4000 by 4000, and its thickness is 575 micron. So, this kind of structure here you can natural frequency is calculated using Cantilever, it is 842 hertz, using analytical technique is 854 hertz. So, analytical means the expressions which I gave you in my earlier slides, using that the relations and taking the value of H1, D naught, B1, A1, you can calculate easily the natural frequency in damping coefficient. In both the cases, either you go for finite element structure or the analytical structure, you can get the values like 842 and 854, which is not wide apart. In damping coefficient 3.83 and 3.87, this is very close, but this damping coefficient is not acceptable because it is not our design value. Design value of the damping coefficient should be nearly 0.7 to 1 or 1.1, and in this is maybe acceptable natural frequency 1, it must be greater than 100 hertz. So, it should not be less than 100 hertz. So, it is greater than, so it may be acceptable, but other two are not acceptable. So, this kind of structure for the single flexure, the capacitive accelerometer, we do not use because it does not meet our design specification. Now, for 10G, again we have calculated the two cases where the beam in center, beam on top. Just I mentioned earlier that the beam which is connected with the probe mass and the frame, it may be at the top or it may be in the center. So, on the top you can see here the 7.1. So, that is delta is this one is a and this is 6.9, although calculation wise is equal, but beam in the center you can see this is 2.1 E minus 6 and here it is 0. That means, here is a 10G in x direction. Try to understand, this is not along z direction. So, in x direction means we do not want any delta. Delta is what? The displacement along z direction. If we apply the acceleration along x direction, that should be as minimum as possible. Okay. So, that we found if beam in the center is a E minus 6 and beam on the top E minus 1. So, obviously, the top one, if beam is at the center, it is better, and in analytical it is almost 0, because it is analytical straightforward the relation if you use. So, the movement along that, if you apply x direction, we assume that z direction is 0. So, that is why it is 0, but some movement along z will be there if you put x direction acceleration. So, that is why in Coventor accept that. So, there you are getting some value which is very small. Delta is the displacement along deflection to the mass due to acceleration 10G in x direction, that is the delta here. So, obviously, if you compare these two values, then always whatever the structure you use, either single beam, single flexure or double flexure. So, we found that if beam is in the center, and center means I mean to say not the center of the length, center means in the thickness wise, not at the surface, but at the center of the cross section. So, there if you do it, so this it is better so far as the displacement as well as the off axis sensitivity is concerned. So, now so for till now I have discussed all the optimization, all the different kinds of structure, either bridge or the cantilever, single cantilever, double cantilever also. Now, we have to optimize the thing. So, out of the three structures, two beam cantilever without perforation, two beam cantilever with perforation, multiple beam bridge type structure. The with perforation, without perforation, why it is coming? Perforation means what? We have seen in the earlier view graph that you can somewhere here damping coefficient. You see damping coefficient here is a 3.83, 3.87. So, that is not at all acceptable. That you can improve by making some holes on the seismic mass. So, now the holes are in the periphery, blank spaces are at the periphery. Now, you can put some holes at different location of the probe mass, that is known as a perforation. Then these through that holes, so air can flow from bottom to top cavity to bottom cavity. So, that will also help the damping coefficient. So, that is why it has been mentioned that a two beam cantilever without perforation, two beam cantilever with perforation, multiple beam bridge type structure. There are three structure now optimized. Single beam cantilever is not acceptable, as I have shown earlier, because that the also in off axis means x and y axis also z displacement is enormously high. So, that is discarded. we go for 2 beam, even in 2 beam, and we have to see which structure gives you better damping coefficient. Okay. So, from there, and multiple beam bridge type structure is again complicated. So, if I get almost similar kind of performance with the 2 beam structure with certain modification, so we always opt for that simplified 2 beam structure with certain modification whose performance may be very close to the multiple bridge type structure. Now, these are some optimized values where 2 beam cantilever without perforation and 2 beam cantilever with perforation, the A1, B1, H1, B2, H2, D naught, these are the parameters, and for 8 beam cross bridge structures, these are the A1, B1, H1, B2, H2, D naught. So, with this kind of the optimized value of the dimension, we can achieve the targeted value, simulated targeted value. So, that is why here since we will not go for the complicated 8 beam cross bridge structure, we can without perforation of 2 beam cantilever, we can concentrate on that and we can make the design using this physical dimension. Now, this is the mass length, using the other the A1, B1, H1, B2, H2, D naught, these parameters we have calculated the values, the sensitivity, nonlinearity, natural frequency, damping ratio, and delta Z at 10G. Delta Z at 10G means the displacement of the seismic mass. So, that we found that the mass length, if you use the mass length is the center of mass and the fixed edge, the L value, without perforation is this one, with perforation is 4000. Sensitivity found is almost in both the cases very close, and nonlinearity is a 0.927 is a 0.89. Here is because desired value is a very good value is 0.8, but it is 0.9 slightly different. 933 hertz, 1.31 kilohertz, and this is a damping ratio here is a 0.835 is a 0.8 here, and delta Z 10G is a 4.12, with perforation is a 2.12 micron. That is the displacement along Z direction. So, here displacement along Z direction without perforation is more compared to with perforation. So, displacement is more, that means you will have the capacitance change also more, isn't it? So, under that condition, although damping ratio is same and nonlinearity you are getting very is less than 1 in both the cases, here a little bit more, that means not that bad as with perforation, but so far as the displacement, this is better. So, we can concentrate on this without perforation 2 beam cantilever structure, that after optimization of different parameters with different dimension, we can now stick to that structure with those values. Now, next is the how a with perforation looks like. That is one picture shown is a basically the not bridge type, cantilever type with 2 flexure and the center some hole is made. Okay, and there with acceleration how it moves, how is the movement along Z direction, it is shown. That is basically the structure with perforation. In cantilever structure, the damping is within limits and can be tailored to meet the specifications by perforation. Hence, it can be used in open loop configuration. On the other hand, in bridge type structure, air damping is very high and hence force feedback configuration is must. You have to go for force feedback configuration in order to settle the complete structure. Besides, measures such as the sealing is required to control the air pressure inside the device. Sensitivity of a bridge type structure is more as compared to the cantilever structure. If you go for a comparison of cantilever versus bridge, these points are coming into the picture. Now, due to the anisotropic etching, the silicon anisotropic etching of silicon, the structure of the beam is not exactly like rectangular, but it will take the form of the hexagonal shape, like the figure it was shown here. The mathematical models were accordingly modified to take into account the hexagonal shape of the beam. So, whatever the analytical expression is given in earlier slides, that is assuming that all the flexure and proof mass are exactly rectangular in structure, not the irregular geometry, hexagonal or other kind of complex geometry. Those complex geometry, if it is there, you have to go for the finite numerical technique, which is a finite element analysis, and that can be done using Coventor wire. There you cannot use the closed form relation analytical expression which is shown in earlier view graphs. Okay. Now, the dimension, now we confine into these values. So, A1 will be 660 micrometer, B1 is 151, that is the width, that is the length of the flexure, H1 is thickness 57 micrometer, and B2 2840, H2, this is B2, H2 is related to the seismic mass. There B2 and A2 are same because square structure we are using 2840, and H2 is a 575 micrometer, that is the substrate thickness, the seismic mass, but the flexure it is 57 micron thickness only. So, that has been etched bulk micromachining, we restricted to 57 micrometer. So, if you concentrate the performance of the structure, it is like that, sensitivity is 0.0012, nonlinearity 0.9%, damping ratio 0.88, natural frequency 899 hertz, deflection 4.48. That all those values are shown in earlier table also, say without perforation column. So, now target specifications has been achieved in the nonlinearity, damping ratio, natural frequency, and sensitivity is also very close. We want their similar kind of sensitivity. So, we can just go for designing, and the delta C for this structure for -1 G to +1 G and -10 G to +10 G is plotted. So, that is shown at say room temperature is nearly 8 into 10 to the power -14 farad delta C change, and for -1 G to 1 G, and for -10 G to +10 G, that is acceleration is +10 G and deceleration is -10 G, is almost, these are simulated values, and there we got these the relations here with those relations. Regular structure we got the delta C values like that, it is of the order of 8.24 into 10 to the -13. For -10 G it is 8.05 10 to the -14 farad in case of 1 G. So, 1 G at 10 G in both cases the two designs has been calculated and simulated, and the values are shown here. C naught means at the rest position the capacitance is 3.4 picofarad, and these are the delta C. With temperature calculation has been made, and there also you can find there is hardly any difference with temperature. That is the beauty or advantage of this capacitive accelerometer compared to piezoresistive. You can see in both the cases the variation is almost negligible, maybe in the third decimal place in 10 to the power -13 farad in that range, almost negligible. Okay. So, now the variation of the xi, that is the damping ratio, that variation is also shown at different temperature, +40 degree C, -40 degree C, +20 degree C, +85 degree C. So, over the whole temperature change we found it is in -40 C it is a 0.729, +20 that is room temperature is 0.898, and +85 1.03. That means we found that it is not wide variation, and these our targeted value of xi was given in the first slide, that was 0.7 to 1.2, and in the whole temperature in -40 to +85 it is within that range. So, we can go for that particular design which we have stated earlier. Now, the two beam cantilever structure has been simulated, and fabrication part has been simulated using IntelliSuite software, that is another software, it is not Coventor. So, IntelliSuite software you can give these process steps and dimension, and there you can see how the structure comes after fabrication. So, there with those dimension what we suggested earlier in our design, that has been applied, and some tentative process steps has been given, and after the process is over, the complete structure, sensing structure looks like this. Here one point I would like to mention, that here in this kind of structure has got the 4 corners. So, all the 4 corners will be etched faster with the parallel as compared to the parallel plane structure, parallel or this either along the length or along the width. So, in that case sometimes here some compensation is given as corner compensation, so that although it is faster at the end, so it should look like almost a square frame. So, that is why some compensation like rectangular piece is added here, so that after etching it will be almost the whole structure will be as rectangular as possible. Okay, if we make it square as possible, and this is at the center of the cross section flexure. Now, here if you want to have at the center, you see this is some diagram is shown. This is the one side is the frame, another side of the mass, and you can see how it is held at the center. So, how can you get that structure? That is again we can use the micromachining steps, which is maskless etching, some kind of thing. So, you can see here, if you etch in this direction, so it will come it will reduce dimension from here to here, and this side also there to there, and that is the crystallographic plane dependence of etch rate. So, that I mentioned in micromachining class. So, that is you use the KOH, the anisotropic etchant. So, that will not etch in equal rate in all crystallographic orientation of the silicon, and we have found the etch rate of 311 plane is 1.71 times the etch rate of 111 plane for KOH concentration of 40%, 48% for temperature in the range of 40 degrees C to 60 degrees C. So, that has been observed, and the inclination angle, that means this angle between 311 plane and the 100 bottom plane is 25.24 degree. So, this kind of etching, how to get this kind of structure is again one important issue which you have to practice, and we are doing so in our laboratory to get the flexure at the center of the cross section. Earlier in piezo resistance case, this kind of flexure is not coming into the picture, that is at the top surface, because there we diffuse piezo resistances on the surface of the single crystal silicon. So, you cannot make the flexure at the middle or middle of the cross section. That is that case we fabricated everything as the top surface, but here as we found that this kind of structure gives better performance. So, we can have certain technique, we have to evolve it, and that is being done to get the structure at the center of the cross section. Okay. Now, this is the thing. So, initial etching with oxide mask over beam is carried out, and subsequent etching is done without any oxide mask. So, first few minutes the etching is done with oxide mask, and after that if you remove oxide, then that rest portion is the maskless etching. Maskless etching means, because some of the crystallographic axis as I mentioned 100 or 311 and 110, the difference is there etch rate. So, that will automatically give you similar kind of structure. Width of the beam in the mask is kept more due to recession during maskless etching. So, you have to think little bit more how the maskless etching is used. The no mask is required to get the flexure at the center of the cross section. So, that has been explored and it can be done. We have seen now in our laboratory this kind of etching is practiced, and I hope within few practice we will be able to get similar kind of structure. Now, after designing, the next part will come is the fabrication. So, that fabrication, again what will be the steps? You can see the fabrication, there are three pieces. One is middle sensing piece, another is the top electrode, another is the bottom electrode. So, all the three pieces are separately fabricated, and at the end you have to bond all the three pieces, and at the same time you have to think contact, how we will take the contact with the top electrode and the middle and bottom electrode and the middle. So, that fabrication details and the making contact of the each electrode and the substrate bonding mechanisms will be discussed in the next lecture. Thank you very much. In my last lecture, I was discussing on a case study on the MEMS sensor, that is MEMS capacitive accelerometer. Some specification we define, and from there how these specifications are achieved, we discussed on that. Two methods we followed, one is analytical treatment and the other is the simulation using standard simulation tools, and we compared the results. I remember I also discussed the various structures of the capacitive accelerometers, which are bridge type, some are the cantilever flexure types. So, out of that we found a particular structure which is double cantilever beam structure is quite sensitive and without much difficulty of technology, and with that we achieved our goal by certain simulation, certain parameter variation, and after satisfying those parameters, our next step will be how to go ahead for fabrication of those devices. And basically these structures are contain three pieces, and how the three individual pieces are fabricated and then how they are assembled, that I will discuss today. The design specifications which I mentioned in my last lecture are range 10 plus minus 10 G, over range 30 G, damping ratio 0.7 to 1.2, natural frequency 100 hertz, nonlinearity plus minus 1% of full scale, a resolution 0.02 G, threshold is 0.01 G, operating temperature range minus 85 to plus 40 degree centigrade. So, with that we confine to this structure which is shown here, three pieces. Middle piece is basically the sensor, and the top and bottoms are two fixed electrodes which form parallel plate capacitance with the central piece, and the central piece is comprising of a probe mass which can move freely between the electrodes, and accordingly the capacitance between top fixed place in middle the sensing electrode and that with the bottom fixed electrode will vary, and we are going to measure the differential change of capacitance of this particular structure. And as we used a probe mass, and that probe mass will displace according to the acceleration, and as a result of which the gap between the gap between two plates will change and capacitance variation will be detected, and which is a measure of the acceleration. Because in the bottom of this bottom electrode, it does not have any insulating layer at the bottom side of the wafer. You have delineated this portion okay, but this side is intact. So, that means one you can take here, one you can take here, and the third you can take either side or from the bottom. That means middle is fixed, from middle and this will give you the one C1, okay, and similarly this and this you will give another C2. this and this will give, because this is the common contact you are making. Okay. So, in this way you can get, after the 3 wafer bonding, you can get the complete thing. The wafer bonding has been taken place, top and bottom. Now, we are joined together, you got the 3 structure. Okay. So, in this way one by one you fabricate separately. Now, the assembly is another very important point in this particular the capacitive accelerometer fabrication, where you have to have the both C1 and C2 top and bottom capacitance contact should be proper, and then you will because you know the C1 C2 both capacitance structure top and bottom will help you elimination of any parasitic or some noise pickup, because you are giving stress on your differential capacitance, difference delta C, C1 minus C2, that is proportional to G. That variation will be with G will be there, and that we are interested. So, in that way, because you see here lot of the conducting planes are there, and if you use the conducting silicon wafer, there is also going to create a problem, because the conducting wafer with another ground plane it will have some parasitic also, and that are the major concern in case of many capacitive accelerometers. So, there we have to see certain design modification, certain techniques, so that those parasitics can be removed completely. Okay. So, this is the complete process sequence of this capacitive accelerometer structure, and I am not going to discuss further on this. And now we will discuss another the inertial sensor. So, that is the gyro sensor. So, we covered 2 case studies, one is the piezoresistive accelerometer, the second was capacitive accelerometer with certain goal and how we designed it, and after design how we fabricate also, that also we discussed in both the cases. Now, I will give some stress on the another kind of inertial sensor, that is the gyro or rotation sensor, and there I would like to give some stress on the quartz gyro sensor with little introduction of silicon gyro. So, next class we will discuss on gyro sensors, MEMS gyro sensors. Thank you very much.